magnetic circuit, you know, one you see on the right here, is made up of, or can be made up of, different materials. So you see, you have cast steel here and mild steel, and it could also be of the same material, but they have different dimensions. So notice that you see the dimensions are different for both these two materials. Um, the cast steel has a smaller cross sectional area, and we don't know what the length is, but probably they are of different lengths. So the composite magnetic circuit, as I say, can be made up of different materials or of the same materials of different dimension. And it may also include an air gap or air gaps. All right. And then the composite magnetic circuit can be connected in series. For example, this one here. And how we know if it's in series? The same flux that is flowing.
Sir,
Yes, sir.
um, is it ear gaps in the material or just ear gaps in the center of the whole circuit itself?
It can be anywhere in the material.
Okay.
Ear gaps really are can be material that are non-magnetic, right? So, for example, in the transformers, you may have some wooden screws, and that would constitute the ear gap. So those material that will probably join material, two magnetic parts of the circuit. Um, because they are non-magnetic, they can be considered as ear. All right, but yeah, good question. All right, so the circuits can be series, parallel, or parallel. All right, so another series circuit shown here, and this one now I show you have it has three parts, part A, part B, and part C, and again the same flux would be flowing through all of the material, so that makes it a series circuit. All right. Now that magnetic circuit, remember we spoke last time about reluctances. So the flux will experience some kind of resistance as it flows through the material. And the reluctance, as we had found last week, was equal to the length divided by mu naught, mu r over A. So the dimensions of the material will help to determine the reluctance. The dimensions and the properties. Now for this magnetic circuit, the total reluctance would be the reluctance of A plus reluctance of B plus reluctance of C. Right. And remember that MMF is equal to S times phi, where S is the reluctance. So you just write in the general equation. So you have different ways of working out the MMF. S times phi, H, the magnetic field strength, times the length, and it's also equal to N times I. And you remember that that current flowing through the number of turns is actually the source of the MMF. Right? And that MMF now drives the flux around. So I could write MMF in terms of the parts now, the reluctance for each part of the material, this magnetic circuit. So it's MMF, the total MMF would be the total reluctance times the flux. Just like how you would have um, total voltage would be equal to the total resistance times the current. Uh, and then I break that out to 5 times SA plus SB plus SC. All right, so similar to an electric circuit, which has a volt drop across impedances, the magnetic circuit also has a what I would call an MMF drop across the reluctances. So therefore, the MMF drop across section A would be the reluctance of section A times the flux through section A, and the same thing applies for section B and section C. Right. So for section B, SB times the flux, section C, SC times the flux. All right. So the sum of the MMF drops equal to this is equal to the source MMF. All right. And I stated that before, but I've written it back again. So MMFT is equal to this relationship. Any questions so far?
Yes, sir. That's a quick question. I see in the diagram you have I1, I2, and I3. Just kind of wondering what
No, it's
are
not I, it's length.
oh,
It's
okay.
length.
Okay.
So length, so all right. I think the next slide will clarify that too. So it's length. So L1 would be the length of section A, L2 would be the length of section B, and L3 is the length of section C. All right,
Okay.
good that you asked that. Yes. All right. So when you using the length, you could also use this relationship. The MMF is equal to H, the magnetic field strength times the length. So it could also have been written like this: HA times L1 plus HB times L2 plus HC times L3. So HA again is the magnetic field strength for section A, and the others are similar. HB for section B, HC, the magnetic field strength for section C. All right. All right. Yeah, this shows now a series parallel circuit. And so you see the magnetic circuit here on the left, and then the electrical circuit equivalent on the right. All right. So the source of the MMF is right here. The source of the flux, the total MMF, right here. So you have the total voltage supply here. And then you have flux moving through the material. When it reaches here, it divides. In this case, it divides in two because the dimensions of D and C are the same. So they have the same length and the same cross-sectional area. So that's why the flux, just like our current would divide equally for equal resistances in parallel, the same thing would apply for the flux. So the flux would divide equally. Assume now that these are considered now based on the flux division that the two parts here called side limbs have the same dimensions. All right, and so the analogies here with the electric circuit, current going through here, and resistors of value R, so both resistors have the same value. So the current splits in two when it reaches this junction. All
sir.
right. Yes, sir.
R1 would represent the air gap.
Yes, yes. Right.
Okay.
Right. Right. Um, now that you point out that there's actually another resistance in here, you know. So this R1 now would be including both the ear gap and this part here of the circuit also. This lower part that the winding is around, that is part of the magnetic circuit too. So it also has a reluctance. So R1 is actually the sum of the ear gap plus this section here.
Okay, sir.
All right. Good.
Hold on, repeat that again for me, please.
Uh, exactly what?
When you were explaining that R1 is the sum of the air gap and which other part?
Right. So the ear gap is a reluctance. It offers very high magnetic resistance to the flow of flux, right? But this part of the magnetic circuit too, what that the winding is around, also has a reluctance, right? So
Okay.
this, right. So the total reluctance would be the reluctance of these magnetic parts here, the metallic parts, plus the ear gap resistance. Okay.
Yes, sir. Yes, sir.
All right. Okay. Good. All right. So I put these two, this picture here together, this diagram, um, in the presentation, so that you can maybe quickly associate the magnetic circuit configuration with that of an electric circuit, and then you can, since you know that already, you can work with that. All right. All right. So let's look at an example, a fairly simple one. All right. So this says now that we have a magnetic circuit here below. All right. And for this magnetic circuit, we see that it's made up of silicon iron, and there's also an air gap. Right. So there are two reluctances in series then. So the length of the silicon iron is 20 centimeters, and the length of the ear gap is 1.5 millimeters. All right, so there are also 3,000 turns of conductor, and a current is flowing through it. That current is what produces the flux through the magnetic circuit. All right, and we can use this magnetizing curve, the magnetization curves. One of them are in here. The one for silicon iron would be this one. All right. So when we need to use it, we will get there. All right. So let's get into the solution. All right. So what I've done again is to put another electrical circuit analogy to the magnetic circuit, right? So your source of MMF, and this would be the silicon steel reluctance, and this would be the air gap reluctance. And in comparison of voltage source, current flowing through one resistance of the some circuit, some component, another resistance, right? And flux flowing through both resistance. So just drawing this picture to your attention again, so that you know again have an idea as to what the circuit looks like. All right. So I think I made a note of that. The equivalent magnetic and electric circuits are shown in the figure to the right. In the magnetic circuit, the reluctances of the silicon, iron, and the air gap are shown connected to a source of MMF. And the source of the MMF now would be the current in the coil.
Sir, question.
Yes, sir.
Is there a reason why I use the DC representation for the circuit, the electric circuit?
All right. Well, the assumption here is direct current.
Oh,
All
okay.
right.
All right.
So the assumption is direct current.
Okay. All right.
All right. But it would apply if it was AC, just to see it. So.
Okay.
Sure.
I'm thinking that the field, I don't, would the field be stationary like the DC? No, I don't. That's what I'm trying to connect.
But yeah, it as long as the current is there, the flux will be there.
Mm.
So
Okay.
remember, so as long as current is flowing, flux is there. So flux would be in the magnetic circuit.
Okay.
The current is on.
So on the magnetic circuit,
Yes, sir.
where what would represent the air gap?
This one. It have a G beside it. So remember, the air gap is a reluctance also, you know. And you will see in a little while that the reluctance can be very high for air gap because air actually offers more resistance to the flow of magnetic circuit. All right. All right. So all right, let's get into the problem. It will show you that it's not very very difficult. Maybe just a little bit time consuming, but not very difficult.
Sure. Just another quick question.
Yes. Yes.
How does the permeability of air as it relates to the magnetic flux relates to the reluctance?
All right. So pure mobility is how do we define it again? All right. So when it is the ability of a material to allow flux to pass through, right? So magnetic materials have very high pure mobility. That means that it allows a lot of flux to pass through. Air itself now has a low pure mobility. So less flux will be allowed through the air. But it still allows flux to pass through the air, you know. It's just that say a magnetic material like iron or steel would probably carry a 1,000 times more the flux that than air would carry for a particular dimension of both. With me?
So I was just wondering if there's an equation that links the two flux with the the permeability with reluctance.
Well, you can see it, you know, because in the formula for the reluctance, S is equal to what? The formula for reluctance?
MMF over
RA.
But even more directly to what you were asking me, we derived that equation last week. S is equal to L divided by mu naught mu R A. So mu naught is the permeability of free space, and mu R would be the permeability of the material itself. So if you multiply mu naught and mu R, you get what is called absolute permeability. Right? So air has a relative permeability of 1. Right? Other materials now are going to have much higher. All right. I think maybe we did ask you to do some example that Had you calculating permeability too? The relative permeability?
Yes, sir.
Right. So you would have seen those values compared to air. All right. All right. So you okay, Mr. Atkins?
Yes, sir. Good.
All right. All right. So the question, what I've done, and I think the bird does it also, is to kind of tabulate the data that you know, because it kind of helps when you're doing your calculations. At least I find that it helps. So for each material, silicon iron has a 20 centimeter length, so it's 20 times 10 to the minus 2 meters, and its cross-sectional area was 3 times 10 to the minus 4 meters square. Let's go back and so right. So the cross-sectional area was 3 centimeters square. Changing that to meter square, it becomes 3 times 10 to the minus 4 meters square. The air gap was 1.5 millimeters, and the air gap would have the same cross-sectional area as the iron. Right? So the air gap would have the same cross-sectional area. So the same area for the flux to flow through. In another question, we talk about leakage. Right? But leakage means that not all the flux that is produced by the current will flow through all the material. All right. So usually we neglect leakage, but when we get on to transformers, we don't. All right. Now they told us in the question that the flux was all right. So the current produces a flux of 0.45 milliwebers in the air gap. Come back. All right, 0.45 milliwebers in the air gap. All right, so this flux then, as we have been saying, since it's a series circuit, it will be the same, both in the iron and through the air gap. All right, so what I do now is to look at each material now. So for silicon iron, I want to find the flux density, since we're going to be using these characteristic curves. The flux density would be phi divided by the cross-sectional area for the silicon iron. All right. And that works out to be 1.5 Tesla. All right. So it's silicon iron. So we go on the graph now and we look for 1.5. So 1.5 is here. And silicon iron is about here. So it crosses it about here. About here. So I said that's approximately 3,250. Right? Silicon iron. Right? Crosses it here. So projecting down, I say about, so here will be 3.5 or 3,500. So it's somewhere around halfway. All right, so I don't with these kind of graphs, I don't expect exact answer, but it must look reasonable still, right? So if you say 3,300, I wouldn't have a problem. All right. So all right, but I say it corresponds to approximately 3,250. So we move on from there. So the MMF then for the silicon ion would be the magnetic field strength, which we just found from the graph, times the length of the silicon ion. So it's 3,250 times the 20 centimeters, 20 times 10 to the minus 2 meters. So the MMF for the silicon ion is 650 amps. All right, and for the air gap, since they have the same dimensions, the flux density for the air gap would also be this. All right, and then we want to find out the magnetic field strength for the air gap. So it's B is equal to mu naught mu r H, and for air mu r is equal to 1. So H for the air gap then is B divided by mu naught, since mu r is 1, and that works out to be this very large number. Right? So the MMF.
Sir, excuse me.
Yes.
In all cases, the cross sectional area would be the same.
And you have to look at it. You have to look at and see where it's connected to, right? So yeah, you have to look at the circuit. But imagine how you should do it though is look at where the flux is, the source of the flux is coming from, and then you assume now that there's no leakage or no fringing, something that I'm going to ask you to look up. No leakage or fringing, so all of the flux that is produced will be flowing straight up through the air gap. So whatever dimension, whatever cross-sectional area it was coming from, the flux will maintain that cross-sectional area when it flows through the air gap. With me?
Okay, sir. Yeah, man, I get it.
All right, good. All right, so remember, MMF is actually a drop, right? A MMF drop. So the MMF drop across the ear is very high. Right? Based on these figures here. Now then the total MMF. So we need basically what this is saying, that we need a strong MMF source to drive the flux through the ear. If there was no ear gap, then you would see adding back the small length for the ear gap would have somewhere maybe around 660 amps. The total MMF. If there was no ear gap, the total MMF probably would be around 660. But because there's an ear gap now, we need much more force, magnetomotive force, to drive the flux through the magnetic circuit. So this is what this is telling you. All right. So we have found the total MMF, and it works out to be this value 2,440. And remember again now that the total MMF is equal to N times I, and the question had asked us to find the current that would drive that flux. So the current then will be the total MMF divided by N. So it's equal to 0.813 amps.
Sir.
Yes.
The unit for the MMF is ampere turns, right?
Well, some people say that, but it's really ampere turns. Is not a SI unit.
Yeah, it's
right.
Also,
some. Sorry, you go ahead.
No, I'm saying because it's not a SI unit, you just put the amperes. Right.
So in some books, and Hughes mentioned it, that some people would say ampere turns, but turns is not a SI unit, so it's just we just write amperes.
Okay, sir.
All right. All right. Any question about that one before we get into another one? All right. So let's get into the second example. So this, I think the first example came from the bird. This one is now from the Hughes. All right, and it has an electromagnetic has a magnetic circuit that can be regarded as comprising three parts in series. A length of 80 millimeters, and see, I put them in the table already. Cross-sectional area 60 millimeters square. Section B has a length of 70 millimeters and a cross-sectional area of 80 millimeters square. And section C, which is the air gap, has a length of 0.5 millimeters and a cross-sectional area of 60 millimeters square. All right. Parts A and B are of a material having magnetic characteristics given by the following table. All right. So these values can actually plot a graph, and you could use it to plot a graph. But I'm going to show you how you can also use this data without actually plotting the graph. All right. So the question now asks us to determine the current necessary in a coil of 4,000 turns wound on section B to produce a flux of point a flux in the air gap a flux density of 0.7 Tesla. Right? And it says that we should neglect magnetic leakage. All right. All right. So the solution. So part of the solution is for me would be putting in the data in a table. I mean, it's not compulsory that you do that, but I think it helps to organize your thinking and your solution when you do that. All right. Now, since the magnetic circuit has three parts connected in series, then the flux phi is the same in each part. All right. And neglecting magnetic leakage is saying that all the flux produced is flowing through the magnetic circuit. All right. Also, if you look at the dimensions, you'll realize that section A and section C have the same cross-sectional area. And if they do, then they would have the same flux density. All right? Because remember, flux density is equal to the flux divided by the cross-sectional area. So it's the same flux flowing through both of them, through all of them. And A and C have the same cross-sectional area. So we already know what the flux density is for section A. All right. So those are some preliminary information that we have picked out of the question. All right. Now we will need to find the total flux for some more calculation. So I found it right off. So the total flux then would be phi and is equal to B times A. And B we know for section C was 0.7 and the cross-sectional area for section C was 60. So we know that the flux then would be 42 times 10 to the minus 6 Webers. So that's the flux that will be flowing through each section of the magnetic circuit. All right, so this time now I start with section C. Yes.
So if it's a series circuit with different sections, once you find one flux, you find all flux.
Right. The flux is the same right throughout.
All right.
Right, but remember now that as you will see, the flux density can be different depending on the dimensions.
Okay.
All right. So let us look at section C, the air gap. Again, because we use, so B is equal to mu naught mu RH, and mu R is equal to 1 for air. All right. So notice that I don't just make mu r disappear. You know, I tell you why it disappear. Right. So if you give me this, something would be. If you just give me this alone, like b is equal to mu naught h, something would be missing in my mind, and I will try to figure out where it has gone. So help me find out where it has gone by making a statement like this.
Also, sir, if another, if it's not here, it would give us the mu r, right? It would be given
So
in the question.
no, not necessarily, no, but you have information that you can use to solve the problem. As we go through this one, you'll realize that that is why you have the curve too, because mu r for different materials, for magnetic materials, is not a constant. I think we spoke about that last week too,
Yes, sir.
and it varies right throughout, right? It varies depending on the magnetic field strength and the current that is flowing through the coil and all of that. All right, but you will see how you can deal with it without knowing what mu r is. But for here it is kind of special. We know that it is one, so it reduces some of the complication. We don't have to use any tables or any graphs for here. We just go straight to this formula to find the magnetic field strength. All right, so the magnetic field strength based on the data in the problem, B is 0.7 and mu naught is 4 pi times 10 to the minus 7. So for here, the magnetic field strength is 557,042 ampere per meter. And then the MMF across the ear gap will be the magnetic field strength times the length of the ear gap. So that works out to be 278.52 amps. All right. So we know one MMF drop already. That's across the ear gap. All right, let's go to section A now. The flux density, as we had deduced before, is 0.7. Since section C and section A has the same cross-sectional area. All right, now we have to use the magnet for section A. They told you that the table represented its magnetic characteristics, so we have to use data in the table now. So the magnetic characteristics for section A is described in this table. Now from the table, we can see that when B is equal to 0.7 T, we actually don't have any exact value for it here, right? Because the table only have B's going up in 0.2s, so we don't have a 0.7. But B would be somewhere here between 0.6 and 0.8. That means that the H would be somewhere between 340 and 500, right? Just picture the graph, the BH curve. So, and this is what this is saying. So 0.7 is actually exactly halfway between 0.6 and 0.8. So we expect now that H will be exactly halfway between 340, this 340 here, and the 500. All right. So the 0.6 corresponds to the 340, the 0.8 corresponds to 500. So 0.7 is going to be corresponding to somewhere halfway between these two values. All right. 0.7 is halfway between 0.6 and 0.8. So H, the corresponding H, is going to be exactly halfway between.
Sir.
Yes.
Sir, me agree, sir. Because the top number is not linear going left to right,
Yeah. All right. Good point. We can actually find it out, but we actually make an assumption that between these two adjacent points, any two adjacent points, you have a straight line between them.
All right.
So between 100 and 210, you have a straight line. Between 210 and 340, there's a straight line. Between 340 and 500, there's a straight line. and so on. So
Okay.
between these two adjacent points, you have a straight line.
All right, sir.
All right. So yes, we have to make that kind of assumption. Let me see if we can go back. So basically, if you look at these now, you can see kind of straight line going up for these,
Okay.
right? Until when them start to saturate, right? So basically, we were going up somewhere along these kind of lines here on the straight line part,
All right. So that side would be okay. Yeah.
right? Right. So is when them start to saturate now, then it won't be exactly linear, or it won't go up at the same rate.
Mm.
But we still assume between each adjacent point that there's a straight line.
Okay.
You can see a straight line
Mm.
between points here still, right?
All right, sir.
All right. All right. So yeah, that is something that you need to bear in mind. I think I made a point about it too, and you will find that when we're calculating for section B, is gonna we're going to be using that. But I won't bother with this kind of um, deduction. There's a more exact way of doing it called interpolation. All right. So I guess
Yes,
you
sir.
can practice
But I like that thing there, no, sorry.
interpolation.
You prefer assume.
uh, yeah, the interpolation gonna assume that you have a straight line between adjacent points.
All
All
right.
right. So yeah. All right. So if we interpolate, we will actually get the same values, right? Because we assume a straight line between here, so the gradient anywhere along here is going to be the same, right? Gradients along anywhere between these points here is going to be the same. So it works out to be this, the 340 plus half the difference between these two, since it's exactly halfway. So it ends up at 420 ampere per meter. All right. So this is not a way that I would normally do it. I would do the interpolation. Uh, but I want you to realize that you can, for when it is kind of straightforward, you can look at it and make some deductions also. All right. But if it's not straightforward, as when we get to section B, then you will see how we deal with it. If you want to be on the safe side, do it like how we're going to do in section B.
All right, sir.
All right. So continuing for section A, the MMF for section A is equal to HA times LA, and that's 420 times the 80, the length, 80 millimeter. So the MMF for section A is 33.60. So you notice the difference between the ear gap and the metal, right? A larger MMF drop to push the flux through the ear than what is required for the metal. All right, so let's move on to section B now. So section B, its flux density is given by phi divided by the area of section B, and that works out to be 0.525 Tesla. All right. Now, again, section B is
Sir,
yes, Miss Montague.
sir, I don't know if you've changed the slide, but I'm still seeing the table. I'm not seeing what you're talking about. I'm still seeing the table with the different sections and their
You're not seeing
properties.
anything on the right.
I'm not seeing section B. I'm seeing for section C and A.
Oh, I wonder why.
I'm not sure if it's on my side or yours.
You see section C, and anybody else seen what she's saying? Because I have section B
No,
on
sir.
my.
Me I see a mouse and move and everything. Everything alright.
Section B. All right, check again. I don't know if there was some kind of freezing a while ago for yours.
I'm only seeing C and A, sir, not B.
Try and restart the stream.
Oh, you do that?
No, sir, not you, sir. Not you.
Yeah, no,
You're
I
fine.
still wondering for her how she would
Oh,
restart.
just go, come out and come back in, sir. Just leave it and then come back in.
All right. Well, try that then, no? It's Montague.
Okay, sir, I'm seeing it now.
Okay. All right. Good. I don't know what happened. All right. So the flux density for section B, phi divided by the area for section B, works out to be 0.525 Tesla. Right. And now when you look at again the magnetic characteristic for section B is also described by the table. Now, if you look at the table, you'll realize that there's no 0.525 here. There's not even a 0.5. So this time now it is not a halfway between. So what we have to do now is to work out, interpolate what the corresponding value of H would be for B equal to 0.525. So we know already though that with the 0.525 is going to be between 0.4 and 0.6. So therefore the H is going to be somewhere between the 210 and the 340. We're going to assume, Mr. Campbell, that between these 2 points there's a straight line. So we're going to interpolate. All right. So when we interpolating, we're actually assuming that the gradient is the same anywhere between these 2 points. It's a straight line. So, you know, a straight line, the gradient is the same anywhere along that straight line. All right, so we use that now. So let H be corresponding to B equal to 0.525 Tesla, and we do the interpolating. So basically, we are finding the gradient of 2 different sections of the same line. All right. So on the right is the whole line between 0.6 and 0.4, or the section of the line between 0.6 and 0.4. Remember, it's BH, so B would be on the vertical, H would be on the horizontal. So it is basically the difference in vertical height over the difference in horizontal length. All right. So rise over run, basically. So between 0.6 and 0.525, we have these corresponding values. So 0.6 correspond to 340, and HB would correspond to the 0.525. All right, but we know what the gradient of the line is from this part, where we know the line is between 0.6 and 0.4, and 340 and 210. So we can work out what HB is from this equation. All right. So just some mathematical manipulation will bring you down to this, that HB is equal to 291.25 ampere per meter. All right. So it's just mathematics, basically gradient, working on gradient, and finding the corresponding HB point between these 2 points.
But we can draw the graph, right?
Of course you can.
Yeah, man.
Of course you can. You are the first person in all of the years that I've been teaching it that want to draw the graph.
That's quite fine.
Because everybody else seems to be afraid of drawing graphs.
You don't want to draw. You don't want to draw.
It does make more sense.
I don't want to draw in the graph.
Yeah. Well, this is an easy way of solving it if you don't want to draw the graph and then read off, because you have to be fairly accurate too. But I mean, the values are whole numbers, so for H, and these are fairly uniform. So it's an easy graph to draw. You know, I would probably quickly draw the graph too, but I'll show you another way. All right, how you can determine it also. So this is the other way. Instead of drawing the graph, you calculate like this, and then HB works out to be 291.25, and the MMF across section B then would be HB times LB, and that works out to be 20.39 amps. All right, so the total MMF for the magnetic circuit, MMFT, would be equal to MMFA plus MMFB plus MMFC. And when we add up all of them, we get 332.51 amps. All right. And then the total MMF is also equal to N times I. Therefore, I will be MMFT over N. And the 332.5 divided by 4,000. And we get 0.0831 amps. And I think the textbook had it as 83 milliamps. So I write it in terms of milliamps. But if you had left it in amps, that would have been okay for me.
Sir.
Yes.
Stupid question. Very stupid question. Why we have the air gap again?
No, well, it's part of the construction of the material, you know. As I was saying, that in magnetic circuits, like for example in a transformer, right? You may have non-magnetic materials inside connecting magnetic materials together, like a wooden screw, for example. So the magnetic material is joined by non-magnetic material, and the non-magnetic material now can be considered similar to air.
Okay.
All right. So air gap is really a general term for non-magnetic part of the circuit. All right. All right. So I think this is your question that I've posted in the classrooms, both classrooms. So you have about, all right, this is 6:07 now. So you have at least another hour to work on this. I will post the slide, the PowerPoint presentation in the classroom too, so you can go back and refer to it. But you have approximately 50 minutes now to work on this, so you should be able to complete. But just in case you don't, then you have until midnight to do it. Scan and upload. If you can, I would prefer that you save it as a PDF because I can actually write on that or make comments on that. If it comes as a picture, say that again.
This is part of the 10% assignment.
You could say that, yes. Yeah, yeah.
All right.
All right, sir.
All right. So, right. So that is the question. I've put some other things that you can practice. Although I say homework, you don't really have to submit it to me, but you should use it for practice. Right. But there's something that you need to review or research. I've mentioned them briefly a while, during this presentation. Fringing. So you need to know what is fringing and what is magnetic leakage, because the flux doesn't normally just follow the path that it's actually coming from. Things happen in the circuit, and those include fringing and leakage. So you can read up on those because we will meet them again later. All right, but you should be able to explain them. You will find diagrams that explain them too.
Sir,
Yes, Miss Montague.
did you send us this PowerPoint?
I'm going to send it to you now.
Okay, sir.
You want me to send it to you now?
Yes, sir.
All right. You know, I was tempted to send it, but I don't want to stress you with everything one time.
Well, sir, if you say go, you send them before class. So.
Yeah, I had it about 3 hours sitting down and wondering, should I send it? Because you might just get confused.
Sir, should I send it with the assignment, sir?
All right. I expected you to say that. All right. So I will send it now. We can actually stop now, so that you have time to work on it, and everything.